Okay, so this is I guess, our fourth online lecture, and so we're going to today be finishing up the material from chapter 8. And so the first material we looked at from chapter 8 involved studying certain linear recurrence relations. So part 2 of chapter 8 is a little bit unrelated, so we're going to go back to talking about counting problems. And what we'll be focused on is a more sort of general version of the inclusion-exclusion principle, which was introduced a few weeks ago. Right. And so what I wanted to do first was just quickly review the two versions of the inclusion-exclusion principle that we already know from previous lectures. And so remember, well, what is the inclusion-exclusion principle? It's basically a way of counting the cardinality of the union of a collection of sets. So let's, for example, suppose that we have three sets, A, B, and C, and suppose they're finite. So remember that we can calculate the cardinality of A union B by adding up the size of the individual sets. But when we do that, well, we're counting the region in the intersection twice, so we have to subtract that off. Right, and so that's the inclusion-exclusion principle for two sets. And we also saw a sort of a more complicated formula for three sets. And so how did this work? Well, if I take the union of A, B, and C, I can calculate the cardinality of these three sets by, well, I can add together the three cardinalities of the individual sets, but then I have to subtract off each of these terms, because you can see if you look at particular examples, you can see that in each of these terms is being counted twice in this sum, so I have to subtract each of them off because I've already counted them too many times. But when I subtract these three off, what's going to happen is you're going to actually subtract off everything in the triple intersection of the three sets, so you have to add that back in to make up for it. And so a good way to look at this is in terms of the sort of a Venn diagram picture. And so you can see this figure here describes sort of why you need each of the terms in the inclusion-exclusion formula. So for example, if I look at the first image in this picture, and so if you sum up the cardinality of A, B, and C, this little picture tells you in each region how much of this region you're counting, right? So if I'm in A alone, and I have an element of A that's not in B and also not in C, well, of course I only count that once. But if I have an element that's in A and also B, but not in the intersection of all three sets, then I count that element twice. And similarly, if I have something that's in A and C, but not in B, I count that twice. And if I have something in C and B, but not in A, I count that twice. And then if you go into the middle and look at the set of elements that are in all three sets, well, I've counted those three times. And so to sort of correct for the fact that you're counting these things too much, well, the first thing you want to do is subtract off intersection of A and B, subtract the size of intersection of A and C, and also subtract the cardinality of B intersect C. And what that does is, well, in each of these pieces where I was counting twice, that makes up for it, corrects the error, and in each of those regions, I'm now counting only once. But then in the middle, where you're looking at elements that happen to be in all three sets, well, I've subtracted too much, right? So now I'm counting those 0 times. And so in order to make up for that and correct the error, I just have to add back in the cardinality of the intersection of the three sets. Right, and so this gives a good sort of pictorial way to understand, using a Venn diagram, why this inclusion-exclusion formula holds. So I did not design this picture, I just sort of ripped it off from the internet, but I think it's a helpful way to understand the formula in the case when you have three sets. And so what we're going to be doing in this lecture is considering inclusion-exclusion, not just when you have three sets, but when you have just sort of n sets, where you have a list of some number of sets and you want to calculate the cardinality of the union in terms of things that look like this. But before I do that, let me just quickly sort of go through an example of how we would apply the inclusion-exclusion with three sets, just to remind us how these sorts of arguments work. Right, and so this is an example where, let's suppose we have, say, 2,421 students at the University of Illinois, and these students have taken a class in either algorithms, discrete math, or logic. And let's also suppose that 2,032 of those students have taken a class in algorithms, 1,300 have taken a class in logic, and 1,850 have taken a class in discrete math. And suppose we also know a little bit more information. So suppose we also know that 1,082 have taken both algorithms and discrete math, that 900 of the students have taken both discrete math and logic, and that 872 students have taken both algorithms and logic. And so the final question is, given all this information, how many students have taken all three of the classes, right? How many students have taken algorithms, discrete math, and logic? And so, of course, we're going to be able to answer this by using the inclusion-exclusion formula for the case of three sets. Right, and so what are the sets going to be? Well, they should hopefully be clear from the problem statement. So let me use A to denote the set of students who took algorithms. Let me use D to denote the set of students who took discrete math. And let me use L to denote the set of students who took logic. Right? And so, well, what are we trying to calculate? We're trying to calculate how many students took all three. Well, the number of students who took all three courses is by definition the cardinality of the intersection of the three sets, right? Because the intersection of the three sets is just students who took A, D, and L, right? So we want to count the number of those students. Right? But remember, by inclusion-exclusion for three sets, we have this sort of complicated formula. But the thing that's helpful is that this formula involves the quantity we're trying to calculate, right? It involves the cardinality of the intersection of these three sets, plus a bunch of other terms. But for this problem, we're actually told what each of these other terms is, right? And in particular, if you go back into the problem statement at the top of the slide, you can see that each of these pieces of information is given to us, right? For example, why is the cardinality of A intersect L equal to 872? Well, if you go back into the problem statement, we're told that 872 students have taken both algorithms and logic. Well, the set A intersect L, it just lists all the students who took both algorithms and logic, and so the cardinality of that set is exactly 872, because that's what we were told. And so similarly, you can sort of figure out the values of each of these remaining sets. And then if you plug these all in and do some simple calculations, you'll see that you can get that the quantity that we're after the quantity that we're after, or the number of students who took all three classes is 93. And again, it's just sort of, you're given a lot of information, you apply the inclusion-exclusion principle, and you sort of plug in all the terms that you can calculate in terms of what you know. And for this problem, we had enough to figure out the cardinality of the intersection. All right, and so now we're going to move on, as I mentioned a few minutes ago, to the general version of the inclusion-exclusion principle, which is going to be a little bit more complicated. So sort of, we'll try to take it sort of one step at a time without sort of overwhelming things, but just a warning that the formulas will look a little bit complicated to begin with. So let's say I have a list of n different finite sets, say A1, A2, up to AN, where n can be any number you want, not just 2 or 3. And so the question is, well, what is an inclusion? What is an analog of the inclusion-exclusion formulas for larger n? And so what is a formula we can use to calculate the cardinality of the union of these n sets? Right? And so the main theorem, which we'll prove and then look at some examples of, some example applications of, is the following. So if I want to calculate the cardinality of A1 union A2 union A3 up to AN, I can calculate it by instead considering the following sort of complicated looking expression, where I have the first term is just the sum of the individual cardinalities. And then in the second term, what I'm doing is I'm subtracting off the cardinalities of all the individual sort of pairwise intersections. Well, to make up for that, as we saw in the case when n is equal to 3, maybe you subtracted off too much here, so you have to add back in the things that you were counting too much. And so I'm adding back in all possible triple intersections of sets from the collection, and so on. And then you have to go to all possible intersections of 4 sets, and then possible intersections of 5 sets, and so on, until you finally hit the end, which is just the intersection of all n sets. And so it should not, you can sort of see there's some sort of formal similarities between this formula and what we saw in the case when n was equal to 3, for example. But otherwise, there's certainly no obvious reason why this formula is the case, and it should be sort of mysterious right now. But what we're going to do is sort of actually prove that it works, right? So if you don't immediately see why this works, that's okay, because it's a very complicated formula. Right, so I just wanted to, before we sort of jump into the proof of this theorem, I just want to illustrate this with a particular example, in particular because maybe a lot of you aren't familiar with this summation notation, right? So what does it mean, for example, in this third term here to sum up over all I, j, and k satisfying these inequalities? Well, this means that I'm looking at sort of every collection of 3 sets, say one choice is say AI, AJ, and AK. Well, why do I need this ordering? If I allow, for example, I less than J, and then I sort of consider when J is less than I, I'm just counting that too many times is sort of the idea. Right, so by symmetry, you only need to consider the special case where the indices are increasing, because otherwise you'll just, if you add in the other terms, you'll just be counting those again, which you don't want to do. Right, and so it'll help to sort of expand out the case n is equal to 4. So what does this formula mean when n is equal to 4? Well, I have the first term, which is just the sum of all the 4 sets, which is clear. The second term, this means I subtract off the cardinality of the intersection for each possible pair, where the first index is less than the second index. Right, so I subtract off cardinality of A1 intersect A2, minus the size of A1 intersect A3, minus the size of A1 intersect A4, right? So that's when I is equal to 1. And then when I is equal to 1, J can be 2 over here, 3 over here, and 4. And then you move up to I equals 2. When I is equal to 2, well, J has to be bigger than 2, so we're considering A2 intersect A3, and also A2 intersect A4. And then finally, we can have I equal 3. If I is equal to 3, there's only one more term, which is when J is equal to 4, and so we're subtracting that off as well. Right, and so again, why don't I want to take I equal J? Well, if I take I equal J, then I'm just counting one of these terms that we already did, right? Because the intersection of, say, for example, A1 with itself is just A1, and we already counted that here. On the other hand, why don't I want to take, what about if I switch the inequality and think about, for example, why can't I equals 2 and J equal 1? Well, if I is equal to 2 and J is equal to 1, the set is the same, right? A2 intersect A1 is the same as A1 intersect A2. And so I'm already counting those terms here, right? So I don't need to consider the case when J is less than or equal to I, right? Right, and so those are all the terms with 2 sets, and then you move on to the terms with different choices of intersections of 3 sets. So in that case, you can have A1 intersect A2 intersect A3. This is when I is equal to 1. You could have A1, A3, and A4, again, when I is equal to 1. And those are the only possibilities when I is equal to 1. Now, if I is equal to 2, there's only one possibility. You can have J equal 3 and K equal 4, and that's it. Right, so there are 3 terms for corresponding to the sum here with 3 elements. And then finally, we're just left with the intersection of all 4 sets. So you subtract off this last term. Right, and so, well, I mean, even looking at the formula when n is equal to 4, it should not be clear at all why is this actually the case? Like, why does this formula work? So let's actually move on and try to prove it. And so it is possible to prove this formula just using what we know. Like, we know the formula when n is equal to 2. We also know the formula when n is equal to 3. And what you can do is sort of guess the correct form, which is what I had in the theorem before, and then prove it using induction. I don't think, although it's not too hard to make the proof work using induction, I don't think it's sort of the most insightful argument that sort of explains, well, why does this formula actually work? And so in order to understand why this formula actually works, it's better to use a more combinatorial proof, which is what we're going to do. Right. And so Right, so let's just sort of recap what we're trying to do. We have n different sets, say A1 through AN, and we're looking at the cardinality of the union. And we want to show that this cardinality is equal to this sort of complicated expression that I've copied to this slide. And so what are we really doing? Well, we're counting the number of elements in the union of these n sets. So let's just suppose we have one element that's in the union, meaning A belongs to at least one of these sets, possibly more than one. Well, what do we have to show? It suffices to show that if we look at this complicated formula over here, that it's only going to count little a exactly once, right? So if I add up all of these terms, then subtract all of these terms, add up all of these, and so on. In all of this work, I'm only counting a exactly once, right? I'm not counting a 0 times, I'm not counting a twice, right? Just counting a exactly once, right? Because if this is true for each a in the union, and if this term counts each element of the union exactly once, well then this complicated number over here has to just be equal to the cardinality of the union, because well, it's counting out every element in the union exactly once, right? So it's just counting the number of elements of the union. Right, and so we can make one more assumption, right? So remember that if I have some element of the union, well, by definition, it belongs to at least one of the sets. And so there's some largest number R, right? So it will belong to exactly R of the sets from the collection, right? So it may not belong to A1, A2, A3, A4 up to AR, but there's some subset or subcollection of our sets for which A belongs to, right? So for example, maybe this element A belongs to A1, A4, and A7, and so in that case, we're taking R equal 3. Right, so I'm not saying they have to be in order, it's just some sub collection of R sets. There's some number R between 1 and n for which A belongs to exactly R of the sets. Right? Right, and so we're going to fix that number R, and using this assumption, we'll complete the proof, and we'll show that the element A is counted exactly once in this list. Right? And so notice before I sort of proceed with the proof, like for example, let's say R was equal to 3. That means that A belongs to exactly 3 of the sets. So let's look at this formula. So the first 3 terms here involve 3 or fewer sets. So it's possible that each of these 3 terms is counting A some number of times. But as soon as I start looking at intersections of 4 or 5 or 6, etc. sets, well, it's not possible for my element A to belong to an intersection of more than 3 sets if R is equal to 3. And so all those terms are 0. And so we only really have to consider the terms in this complicated formula that go up to where you have intersections of R sets rather than intersections of N sets. However, it may be the case that maybe the element I picked, this element A, belongs to every single set, in which case you do have to count everything in the formula, right? So the formula, there's no vacuous terms in the formula. It's just that for certain R, some of the terms may be 0, which we'll take advantage of in the argument. Right, so what we're going to do is just do this term by term and see, well, what does each term count? And so the first term, when I'm just summing up the cardinality of all of the sets, well, if my element A belongs to exactly R of these sets, then this sum counts A exactly R times, right? And I can write R as R choose 1 for a reason we'll see in a second. Right, so hopefully this is relatively straightforward, right? There are exactly R out of the n sets where I count A, and so that's the number of times it's counted. Right, and so now let's move on to the second sum. And so the claim is that the second sum, which is summing up the intersection or the size of the intersections of different pairs, will count A exactly R choose 2 times. Why is this? Well, consider the list of all the sets that A belongs to, right? This sum is going to count A every time I have a pair of 2 sets such that A belongs to both sets in the pair, right? And so what I'm really doing is, well, I'm counting A every time I can pick 2 out of the R sets that A belongs to. Well, if I'm trying to pick 2 out of the R sets for which A belongs to, that number is just R choose 2, right? Right, this sum is only counting A when there is some chosen pair of 2 sets from the collection of R sets which contains A, right? And so this will count A exactly R choose 2 times. Similarly, if I move on now to the third sum, right, where I'm looking at the sum of triple intersections, well, this is only going to count A if every single one of these 3 sets contains A. And so I'm picking, so I'm counting the number of triples from right, so I'm counting the number of ways to pick 3 sets from the list of R sets, which I know contain A. Right, and so this is, again, using sort of a similar argument, this term is going to count A exactly R choose 3 times. And so on, right? So if I go now to the case with 4 terms, well, then I'm counting all the quadruple intersections that contain A, which is equivalent to picking 4 out of the R sets for which A belongs to, right? And so the number is, again, going to be R choose 4 in that case, and so on. And so if we continue this argument and we do the same sort of analysis for each term, we'll see that this complicated expression will count the element A exactly this many times, right? So for the first term, I had R choose 1. The second term is counting A R choose 2 times, but we have a negative sign, so I'm subtracting that off. The third term is counting A R choose 3 times with a positive sign, so I add that on, and so on. And so we get this alternating sum of all these different binomial coefficients where the number on the bottom ranges from 1 through R, and this is how if you can match up the signs, this is how the signs work. Right, and so notice, right, once this number in the bottom part of the binomial coefficient is bigger than R, right, remember, as we mentioned briefly in the remark before the proof, we don't count, none of those terms can count A, so those are all counting A 0 times, so we don't need to worry about those terms. Right. Right, and again, we're very strongly using the assumption here that A belongs to exactly R of the sets, right? Okay, and so, right, let's recap where we are. This expression involving the binomial coefficients tells me how many times the inclusion-exclusion formula counts one particular element A, assuming A belongs to exactly R of the sets. And so to finish the proof, we have to show that this number is 1. Right? Remember, we wanted to show that this formula counted A exactly 1 time. Right? And so in order to show that this number is 1, we just have to use the binomial theorem. And so the way this is written should remind you of the binomial theorem. And so in particular, remember that if I sum up the binomial coefficients times -1 to the k, as k ranges from 0 to R, by the binomial theorem, this is just equal to 1 minus 1 to the power of R. But of course, 1 minus 1 to the power of R is 0, right? So this alternating sum on the left-hand side is always equal to 0, no matter what R is. And so if I rearrange the sum, we can sort of deduce the following formula. Well, here I'm just sort of writing out this summation notation in a different way. And now let me rearrange this formula, and you'll get that, well, if I bring over all these remaining terms except for R sub 0, R choose 0 to the right-hand side, I get R choose 0 is equal to the expression we had previously counted, right? But of course, how many ways are there to choose 0 elements from R elements? There's exactly one way to do this. R choose 0 is equal to 1. And so the formula that we wanted to show is equal to 1 is equal to 1. And this sort of, again, just follows from the binomial theorem. And so that completes the proof, right? Again, just to recap what we did, we fixed an element A, which was in the union of all these n sets. And we chose this number R, which is the number of sets from the list that A belongs to. And then each term will count A exactly this many times if you look at the formula that I'm hovering over right now. And then using the binomial theorem, you can check that this number, no matter what R is, this number is always equal to 1. Okay, and so that's the proof of the more general inclusion-exclusion principle. Maybe a good exercise would also be to try to prove it using induction, as I mentioned before, although I think understanding this proof is maybe a little bit more insightful because it sort of tells you why the formula works, not just that it does work. Right? Right, and so now in the second part of the lecture, we're just going to talk about some applications of the general inclusion-exclusion formula. So we'll talk about two particular applications. Before we do that though, it helps to sort of interpret the formula we just proved in a slightly different way, which makes it a little bit easier to apply it to some counting problems. And so I'm going to first talk about an alternate form of the result we just proved. And so again, we'll suppose we have n different subsets of a larger set S. And let's suppose that this larger set S has cardinality exactly equal to n, where n is like capital N. And we'll suppose, moreover, that each of these sets, A1, A2, etc., corresponds to a certain property, right? So we'll say that AI consists of the element in S that have a certain property PI, and we'll see some examples of this soon, right? For example, maybe S is a list of numbers, and A1 is the list of all numbers that contain a 1 or in their decimal expansion or something like that, right? Right, and so given this list of sets with properties PI, we're going to, well, let's say I pick a subcollection, say, of indices, say I1, I2, up to I sub k, where this is just some choice of k elements out of n. Well, I'm going to let n of PI1, PI2, up to PIK denote the number of elements for which all of these properties that I fixed hold. Right. Right, so sort of in set theory notation, what is this quantity n of pi1, pi2 up to pik? Right, so this is the number of elements for which all these properties are true, and so I have to look at the intersection of the sets, the corresponding sets, right? Because each of these sets, for example, ai1, consists of elements for which pi1 is true. AI2 consists of elements for which PI2 is true, and so on, up to AIK, which consists of elements for which PIK is true. And so the number of elements for which all of these properties is true is just the intersection of these sets, right? And so I'm basically taking these terms which appeared in the generalized inclusion-exclusion formula, and I'm just sort of using this more compact notation, which connects them to sort of this interpretation outlined above here. Right. And so finally, we're also going to let n of p1 prime, p2 prime, all the way up to pn prime denote the number of elements of the set S for which none of the n properties hold. Right. So these are the elements for which p1, p2, up to pn all don't apply. Right. And so in particular, well, these are the elements for which none of these properties hold. How many such elements are there? Well, I have all the elements in the set S, which is this capital N is just the cardinality of the set S. And then I just want to subtract off the elements for which at least one of the properties hold. Right, well, what is the cardinality, or what is the size of the subset for which at least one of these properties hold? It's just the union of all the A1 up to A2 up to AN, right? Because if I have some element of this union, that means in particular it's in one A sub I, and so I at least know that property PI holds for that element, right? And so if I want to count the elements for which none of the properties hold, I just have to subtract off the cardinality of the union of all these sets, and that's what this gives me. Right? And so now what I'm going to do is sort of plug in this new notation into the general inclusion-exclusion formula. Right, so maybe if you pause the video and go back a few minutes just to remind yourself what the formula looks like, and sort of try to interpret each of the terms in terms of these new quantities, n of pi1, etc. Right? Right, well, if I plug in this new notation to the previous formula, this is what we end up with. Right, so let's say I have a problem where I want to calculate the number of elements in a set where some list of properties fails, what this formula allows me to do is instead calculate the number of elements where the property holds, also calculate the number of elements where two of the properties hold, and so on. And then plugging in all that information to this formula, I'll be able to determine how many elements for which all of the properties fail, right? So I can calculate the number of times number of elements for which the properties fail by instead considering number of elements for which some subset of the properties are true, and then sort of combining those estimates or those counts in this way. Okay, so this is all sort of very abstract and complicated. So let's look at some examples which will hopefully make this formula a little bit clearer. And so for the first example, we're going to return to a more familiar problem, which is this problem of counting the number of non-negative integer solutions to some kind of linear equation like this. Right, so for example, how many solutions does the equation x1 plus x2 plus x3 equal 11 have? Well, if we have no constraint inequalities, remember you can solve this problem by using the stars and bars argument, because this is really just sort of counting the number of 11 combinations drawn from a set with 3 distinct elements, where x1 tells you how many of element 1, x2 tells you how many of element 2, and x3 tells you how many of element 3. But let's say I add in some list of constraint inequalities, and instead of counting all of the solutions, I only want to consider solutions where x1 is less than or equal to 3, x2 is less than or equal to 4, and x3 is less than or equal to 6. And so this makes the problem a little bit harder, right? I can't just use the stars and bars principle or argument. Right, and so what we're going to do is use the previous formula over here, use inclusion-exclusion to count the number of solutions. Right, and so what are the properties we're going to work with? Well, the properties will be obtained from the constraints, right? We're looking at for elements with certain properties, and so there's sort of a natural way to do this. And so we'll say a solution has property P1 if the variable x1 is bigger than 3. We'll say that the solution has property P2 if x2 is bigger than 4. And finally, we'll say that the solution has property P3 if x3 is bigger than 6. Right? And so what are we trying to count? Well, we're trying to count the number of solutions that have none of these properties, right? I don't want property P1 because I want x1 less than or equal to 3. I don't want property P2 because x2 should be less than or equal to 4. And finally, I don't want property P3 because, again, x3 should be less than or equal to 6. Right, so again, the number of solutions we're trying to count is just the number of solutions where all 3 of these properties fail. And so in terms of the notation from the previous slide, we're trying to exactly calculate n of P1 prime, P2 prime, P3 prime. Right? And so what do we do? Well, let's just use the formula we had on the last slide, which is basically the general inclusion-exclusion principle. And right, what does that tell us in this case? Well, it tells us that the quantity we're interested in, which is this on the left-hand side, I can calculate by finding the number of elements n, which is just going to be the number of solutions to this equation with no constraints, right? And then I have to just calculate each of these individual terms, and then add everything together in this way, right? Right, so you may think, okay, well, I've taken, right, I want to calculate the number of solutions where all 3 of the properties fail. And instead of just calculating one thing, now I have to calculate, let's see, 1, 2, 3, 4, 5, 6, 8 different terms, right? There are 8 different terms in the sum. Right, so have I actually made the problem any easier? You may think, well, I've just increased the amount of work I want to do, so why is this a good method? The reason this is a good method is because notice that for each of these terms, I'm counting the number of solutions where I have, for example, n of P1, P2, counting the number of solutions where x1 is bigger than 3 and x2 is bigger than 4. Well, this is actually easier to count than if the inequalities were reversed. And you've had a few homework problems where you've counted solutions like this. right? And so what now you would do is you would find each of these individual numbers using techniques that we already know. For example, by changing variables, which we've seen in a few homework problems, and then by putting all that information together, you would be able to calculate the number of solutions for which all three of the properties fail, right? Right, so the point is that sometimes if you want to count the number of things with a certain property, or the number of things for which a certain property fails, it's actually easier to count the number of elements for which the property is true, and then sort of insert that information into the inclusion-exclusion formula in this way. Right, and you can, if you do all this work, you'll see that the answer ultimately will be 6. So this is all, if you go into the textbook, these are all listed out, and you can solve each of these. You can determine each of these quantities by doing like a simple change of variables, as we saw in the homework in previous exercises, and then also just stars and bars method, or counting combinations with repetition. You can find each of these terms. And right, so we'll do one more application, which is going to be a little bit newer than the last example. And so in order to understand this application, we have to introduce a new definition. So we'll be talking about certain permutations, which are called derangements. And so by definition, a derangement is a permutation of some list of objects that leaves nothing fixed, right? It mixes up everything and it doesn't leave anything in its original position. And so what's an example of a type of sort of combinatorial problem where derangements would arise? So this is something that's known as the hat check problem. And so in this problem, you have an employee at a restaurant, say, that checks the hats of n different customers who are entering the restaurant, but the employee forgets to put a claim number on the hats, right? And so at the end of the day, when the customers return to the employee gives back the hats sort of at a randomly choosing them, right? So some person comes up to get their hat, the employee just reaches in, picks a random one, and gives it to that person. And so the problem is, well, what is the probability that no one receives the correct hat, right? What is the probability that the employee gives back the wrong hat to every single person? Right. And so notice that this is really asking for us to count the number of derangements, right? Because, well, we have n different customers, and to each customer you associate their hat. And so if you consider at the end of the day the order in which the employee, or how the employee returned the hats, right? You can think of this as a permutation of the list of n hats in order. And so, well, what does it mean that no one receives the correct hat? Like, for example, what does it mean that person number 2 doesn't receive the correct hat? That means that hat number 2 was moved to a different place and given to someone else, right? So this really is just counting the number of derangements of a list of n elements, right? Right. And so what we'll do is, instead of sort of solving this problem directly, we'll first prove a theorem about, well, how many derangements are there on a set of n elements? And then we'll apply that theorem to solve this problem, right? And so the theorem is the following. So let me let d sub n denote the number of derangements of a set with n elements. This means that d sub n is the number of permutations of the set with n elements, but the permutations don't fix anything, right? There's no element for which that the permutation leaves alone. It mixes everything up, right? And so the theorem is that the number of derangements of a set with n elements is equal to, well, I have n factorial times this quantity in parentheses, so times 1 minus 1 over 1 factorial plus 1 over 2 factorial, alternating up to 1 over n factorial times minus 1 to the n. Right? And so if you remember a little bit of calculus, you can show that this is about what the number is equal to. It's equal to about n factorial times e to the minus 1, where e is the sort of natural base for the logarithm. And so I'll come back to this at the end of the lecture and remind you why this is true. So the more important part of the theorem is the first equality over here, showing that dn is equal to this quantity. Right, and so let's prove this theorem. in order to prove the theorem, we can assume that the permutations we're working with are just on the set of integers from 1 up to n, right? Because I'm looking at permutations on some collection of n objects. I can label the objects respectively as object 1, object 2, object 3, and so on. And so sort of mathematically, we can just model that using the list from 1 up to n. Right, and how are we going to prove this theorem? We're going to prove it using the inclusion-exclusion principle in the sense that we've sort of the alternate form we've been talking about. Right, and so we'll say that a particular permutation has property pi if it fixes element I from the set. Right, so for example, let's imagine I have a permutation of the set S that leaves 2 alone, but potentially changes everything else. Well, as long as it fixes 2 and it doesn't change 2, even though it can change other things, we'll say it has property P2, right? And so, well, remember, a derangement is a permutation that leaves nothing fixed. It moves everything from its original position. And so the derangements are exactly the permutations for which all of these properties fail, right? Property P1, P2, P3, et cetera, up to Pn all fail. Right, which is just what is written out right here. And so this should indicate, well, we should be able to use the alternate form of the inclusion-exclusion principle to prove this theorem. Right, and in particular, dn is equal, using these particular properties and using the notation from before, dn is equal to n of p1 prime, p2 prime, up to pn prime, right? This is the number of permutations for which all n of the properties fail, which is just what I said a second ago. Right, and so if I use the inclusion-exclusion formula in the alternate form, I get dn is equal to this sort of complicated inclusion-exclusion formula. In this case, capital N is just the number of permutations of the whole set S. So capital N is just equal to little n factorial, right? Because there are n factorial permutations on a set of S elements. And so now what we want to do is try to figure out, well, what are each of these other terms equal to? Like, for example, what is n of pi pj, or what are the number of permutations that fix element I and element j, right? And so before I go into more detail, let's just maybe think about the case, let's say n of p1, p2, right? So how many permutations are there on a list of n elements that fix the first 2 elements, right? That fix element 1 and fix element 2. Well, if it fixes element 1 and fixes element 2, there are n minus 2 more spots, which I'm allowed to freely permute, right? And so, right, how many permutations are there of a list of n minus 2 things? Well, that's n minus 2 factorial, right? But, right, that's just if we fix the first 2 positions. Remember, there are other terms in the sum. For example, maybe I fix position P1 and P3, or maybe I fix position 4 and 7, and so on. So this can happen in a number of ways. So it's not just enough to know how many permutations there are for one of these that fix, say, the first and second element. We also have to know, sort of count up over all possible choices of 2 elements that are held fixed, right? And so that's what we're going to do. And so let me sort of just abstract this a little bit. And let's say I just have a list of m different properties, where m is some number between 1 and n. And so let's look at the term corresponding to the sum where each piece has m properties in it, exactly m properties, right? And so these terms are going to be counting the number of permutations that fix, say, spot I1, spot I2, up to spot IM, where I1 through IM are just some choice of n elements from the larger list, right? So for example, maybe m is equal to 3, and our set contains 10 elements, and then maybe I1 is equal to 2, I2 is equal to 7, and IM is equal to 9, or something like that, right? Right, well, how many permutations are there that fix spot I1, spot I2, up to spot IM, that fix all of these spots? Well, these permutations are fixing exactly n spots, and then they're allowed to freely permute the remaining n minus m spots. And so we're really just counting the number of permutations on a set of size n minus m, which is n minus m factorial, right? And so this term is exactly equal to n minus m factorial. Right? Again, since no matter what this sort of list is, you're always holding m position fixed, and then you're allowed to freely permute the remaining n minus m positions. So you can do that in exactly n minus m factorial ways. Right? But notice this is, again, as I mentioned before, this is just for one choice of m elements. Right, and so the question is, well, how many ways can I pick m elements from a list of n elements to be held fixed? Well, that's just the binomial coefficient, right? Number of ways to choose m things from a list of n is exactly n choose m. And so I have n choose m ways of picking my indices I1, I2, up to IM, right? And so I have to, for each of these ways to pick my list, I have exactly this many permutations. And so if I add these all together, I get n choose m times n minus m factorial. This is the number, the value of the corresponding term in the inclusion-exclusion formula, up to this minus sign, which we have to add in, right? Remember, some of the terms, depending on the value of m, they have plus or minus, which is where this term comes from. And so if I just use the formula for the binomial coefficient, you'll see that this simplifies to minus 1 to the m times n factorial over m factorial. Right, so for example, if I go up to the second term here, so this is the sum involving quantities with two properties. This whole sum is exactly equal to n factorial divided by 2 factorial, right? Because in this case, n is equal to 2. And then this term over here, which involves 3 terms, this is exactly equal to n factorial divided by 3 factorial, and then times minus 1, right? Minus 1 to the 3, which is minus 1. And so this, well, now if I plug in all these values, this proves the theorem, right? Well, what have we shown? We've shown if I plug in the suitable quantity for each of the terms in the inclusion-exclusion formula, we've shown that dn is equal to n factorial minus n factorial over 1 factorial plus n factorial over 2 factorial, and so on until we hit the last term. And then if I just factor out n factorial, we'll get the expression from the theorem. Right? Right, remember we wanted to prove this formula. Right, this is exactly the formula we just derived, but I've just factored out n factorial. So this completes the proof. Right, if you just factor out n factorial here. Okay, and so just to finish up the lecture, let's just explain how to use this to solve the hat check problem. Well, how many possible ways are there for the employee to return n hats? This is just the same as the number of permutations of n hats, which is exactly n factorial. And so we're trying to count the number of ways, the number of derangements from this list of n factorial permutations. Right, well, we just proved that the number of derangements is given by this formula, right? And so what is the probability that we have one of these derangements, or what is the probability that the employee returns all of the hats to all of the wrong people? Well, we just look at the number of derangements divided by the total number of possibilities, right? So we're going to look at dn divided by the cardinality of the whole set of all permutations. Since the cardinality of the whole set is just n factorial, we're just going to be looking at dn divided by n factorial, which is easy to calculate from this formula, right? And so in particular, the probability that no one will receive their correct hat is dn over n factorial, which is given by this alternating sum. Right, and so how do you actually calculate this alternating sum? Well, I mean, you could use a computer to do it, but also if you remember some calculus, this alternating sum, if I use the Taylor series expansion of the function e to the x, and I plug in x equals -1 into the Taylor series expansion, then you'll see that this alternating sum gives a very good approximation of just the number e to the -1. And so in particular, this sum is basically equal to e to the minus 1 up to some small error. And so the probability that no one receives their hat is basically e to the minus 1, which is approximately 0.368. And this approximation gets better as n is large. And so remember, if you remember from calculus, the error is about 1 over n plus 1 factorial, which is a very, very small error as long as n is, say, bigger than 10. Right. All right, so that's the second main example I wanted to look at. So that'll be it for today.